August 15th, 1977. A brief narrowband radio burst swept through the detectors at Ohio State University Radio Observatory. A signal so clean, so anomalous, it was circled on paper with a single word. Wow! It lasted just 72 seconds. No one ever heard it again. For decades, the origin of that transmission remained unresolved. It was traced to a fixed patch of sky in Sagittarius. No known spacecraft, no catalogued comet, no follow-up detection. It was as if something had whispered once, then disappeared into the dark. 48 years later, an object is moving back through that same celestial corridor. 3I Atlas, a massive, vast, forward-biased interstellar body with a chemistry no one fully understands, is retracing an orbital path that, when propagated backward, passes within that narrow 1977 detection window. This is not speculation. It's geometry. The alignment is exact to a level that demands attention, and the timing couldn't be sharper. In just over a week, on October 29th, 2025, 3I Atlas reaches perihelion, directly behind the Sun, invisible to all ground-based telescopes. If something were to change course, if something were to maneuver, that's the moment it would happen. This is where the story begins, the past and present folding into a single trajectory. The 1977 WOW signal has haunted the edges of SETI research for nearly half a century. Not because it was loud, but because it was clean. It appeared on the hydrogen line at 1420.4556 MHz, the exact frequency that many astronomers believe an intelligent civilization might use to announce its presence. It arrived without harmonics, without Doppler drift, without the hallmarks of Earth-based interference. It was there for 72 seconds, and then it was gone. No other signal like it has ever been confirmed from that exact patch of sky. Over the decades, countless explanations were proposed. Interstellar scintillation, unknown satellites, passing comets, even military transmissions, all failed under scrutiny. The signal's strength, narrowband nature, and lack of recurrence made it almost untouchable scientifically. Many filed it away as a one-off event, but now something long invisible has returned to that celestial corridor. In mid-2025, after weeks of high-resolution astrometric tracking, the inbound trajectory of 3I Atlas was reconstructed with unprecedented precision. Teams at NASA Jet Propulsion Laboratory, European Space Agency, and a small independent group affiliated with Harvard-Smithsonian Center for Astrophysics ran backward orbital propagations using multiple gravity models. These included perturbations from Jupiter and Saturn, solar radiation pressure modeling, and minimal outgassing assumptions based on early Coma activity. The results converged tightly. When traced back to August 15th, 1977, the object's reconstructed position slices directly through the WOW signal detection window within the same right ascension and declination to less than 0.2 degrees of uncertainty. That is not a vague match. In celestial mechanics, it's a bullseye. And then there's the timing. The backward propagation places 3 Atlas at that location within a 6-hour window of the original signal timestamp. Even factoring in error margins, the overlap is astonishing. Astronomers have been careful with their language. No one is saying 3I Atlas sent the WOW signal. But the orbital geometry alone forces the question. A hyperbolic object with interstellar velocity, inbound for decades, crossing the exact coordinates of one of the most famous unexplained signals in SETI history, is not something that happens often. In fact, probabilistic models suggest a chance alignment of 0.7 to 1.3%, depending on the chosen outgassing model. In astrophysical terms, that's extraordinarily low. The timeline it implies is unsettling. If 3I Atlas was already on this trajectory nearly 50 years ago, it has been approaching the inner solar system silently, without thermal signature, without radar echo, without being catalogued. It eluded the infrared sky surveys of the late 1990s, which should have easily detected a body of its apparent mass as it passed the Kuiper belt. It remained cold, dark, quiet. Only as it neared Jupiter in 2025 did it erupt into detectability, its coma igniting late, almost unnaturally late, as if triggered at a specific heliocentric distance. This delay is one of the key anomalies driving the debate. Typical interstellar comets, like 2I/Borisov, begin significant activity well before crossing the orbit of Jupiter. 3i Atlas did not. The result is an object with a trajectory that appears deliberately clean. It avoided detection at the outer limits and became visible only when approaching the inner planets, precisely when its alignments began to matter. Critics caution against overinterpreting orbital coincidences. Over decades, even minimal uncertainties compound. Tiny non-gravitational accelerations, from asymmetric gas jets or micrometeoroid impacts, can shift the reconstructed path by millions of kilometers, but even after applying conservative error inflation, 3i Atlas remains inside the WOW signal window. The overlap isn't erased, it persists. Proponents of a technological hypothesis point to this as evidence that the object may not be entirely passive. If something with internal control mechanisms adjusted its course over the decades, even slightly, the precision would be explainable. Naturalists counter that such precision could emerge from a rare but possible trajectory combined with observational coincidence. The unresolved tension between these interpretations mirrors the uncertainty surrounding the WOW signal itself. A ghost of a transmission, and an object arriving decades later along its path. Two anomalies, one in radio space, one in orbital space, now stitched together by mathematics. And this leads to the pivotal question few dared to ask in 1977. Was the WOW signal a random burst from deep space, or the first whisper of something inbound? This is not proof, but it's a breadcrumb on a line that stretches across half a century. And as 3i Atlas nears the Sun, what was once ancient radio noise suddenly feels like a message with coordinates attached. When the narrowband transmission was first logged in 1977, it was seen as an isolated anomaly, a burst of radio energy at 1420 MHz, perfectly clean, lasting 72 seconds and never heard again. At the time, the Ohio State University Radio Observatory had no means to track the source. The fixed dish simply let the sky rotate past its beam. The silence that followed turned a single line of data into decades of unanswered questions. That event had a peculiar signature, a steady tone with no measurable Doppler drift. In astrophysical terms, that's rare. A natural emitter tied to a rotating planet orbiting a star almost always leaves a frequency slope behind. The absence of that drift suggested either a finely stabilized transmission or a motion so precisely aligned with the observer that the shift cancelled itself out. At the time, it was impossible to follow up. The coordinates were noted, the sky was scanned, and nothing came back. Almost half a century later, something is crossing that same corridor in space. Orbital reconstruction shows 3i Atlas moving through the exact right ascension and declination of the original detection zone during that same day and hour of 1977. Its hyperbolic trajectory, moving at nearly 58 km per second, lines up with the geometry required to explain a stationary-looking signal from Earth's frame. This alignment is not vague. It falls inside a 6-hour timing window with spatial uncertainty below 0.2 degrees. Modern radio astronomers have been re-examining the original archival tapes with tools the 1970s didn't have. Advanced noise suppression and coherent stacking methods are revealing faint residual structures that were previously buried in the background. Not a second transmission, but subtle frequency echoes. These could be nothing. They could be interference, but they also fit the pattern of something more structured than thermal noise. What makes this more than a historical curiosity is how well the object's current trajectory explains details that once seemed like coincidences. Its motion relative to Earth at that time would have produced a signal with no Doppler drift. Its position in Sagittarius, along the galactic plane, would have allowed a narrowband pulse to stand out against a busy radio background. And its inbound path suggests it was already on a clean, stable trajectory toward the inner system for decades, without ever being detected by infrared sky surveys. This absence of early detection is itself a puzzle. A body of this scale should have appeared in wide-field infrared or radar catalogues years before its 2025 approach. Instead, it stayed dark until its Coma flared near Jupiter. That timing is what alarms some astronomers. The activation didn't behave like ordinary outgassing. It behaved like a threshold crossing. With perihelion just days away and the Sun about to conceal the object, multiple observatories, Allen Telescope Array, Green Bank Observatory, and Deep Space Network antennas are preparing synchronized listening campaigns. Once the object emerges from solar conjunction, they'll attempt to detect even the faintest emission, using wide-frequency sweeps and long coherent integration times. If the 1977 transmission was tied to this trajectory, then the upcoming window isn't just about observing a comet. It's about seeing whether that pulse was the opening line of something that has been silently coasting toward us for nearly 50 years. Most comets wander in at odd inclinations, cutting across the solar system like unpredictable stones skipping across a pond. Their arrival angles are distributed randomly, reflecting chaotic origins in distant reservoirs of icy debris. 3I Atlas is different. Its orbital plane is nearly perfectly aligned with the ecliptic, the same flat disk on which Earth and the major planets orbit the Sun. That alignment isn't a minor coincidence, it's surgical. Astrometric fits from ground-based observatories and space-based tracking stations have refined its inclination to just under 0.8 degrees relative to the ecliptic plane. That's narrower than the orbital tilt of most main-belt asteroids. Statistically, an interstellar object arriving on such a path without prior gravitational focusing is vanishingly rare. Early estimates place the probability below 0.2%. That number has since dropped as the error bars tightened. The ecliptic is not an arbitrary plane. It's a map of where gravity has organised our solar system over billions of years. Most random interstellar objects arrive from high inclinations, 20 degrees, 40 degrees, sometimes nearly perpendicular to the disk. To slip through the planetary plane with this kind of precision implies one of two things: either an extreme coincidence involving long-range gravitational bending, or a trajectory that was selected, maintained, or at the very least influenced toward this geometry long before it crossed the heliosphere. This alignment doesn't just make the object's path unusual, it makes it efficient. A body moving in the ecliptic has natural gravitational assist opportunities from multiple planets. It can slingshot or alter course with minimal delta V if propulsion exists. For a passive comet, this is meaningless. For a maneuverable object, it's a highway. That's why orbital dynamicists are paying close attention to the perihelion geometry. 3I Atlas isn't diving in from a steep angle and disappearing. It's sliding through the most advantageous plane for sustained solar system operations. In simpler terms, if you were trying to quietly insert something into the inner solar system without detection until the last moment, this is exactly how you do it. There's another layer to this puzzle: the timing of its crossing points. In late September, it passed Earth's orbital distance, not near Earth itself, but along the same plane, just as several other planetary alignments tightened. Mars, Earth, and Jupiter formed a near-linear configuration, effectively providing a multi-body gravitational corridor. This is an astronomer's nightmare and engineer's dream, a route where tiny course corrections can result in massive trajectory changes downstream. Some researchers have speculated about gravitational focusing by Jupiter. If the object passed through a distant encounter decades ago, it could have been deflected into this razor-flat path. But such a capture would have required an equally precise inbound trajectory. A low-inclination approach doesn't appear randomly. It's either the outcome of an improbable natural sequence or deliberate alignment with planetary geometry. And then there's the stability. Unlike most comets, which exhibit chaotic jetting and unpredictable motion as they warm, 3I Atlas has remained astonishingly clean in its trajectory. So far, it has shown no significant non-gravitational acceleration, even as its coma brightened near the inner solar system. It's as if the object is deliberately minimizing perturbations, maintaining a smooth glide along the ecliptic plane. This precision is beginning to split the scientific community. Orbital mechanics teams at NASA Jet Propulsion Laboratory have published conservative analyses suggesting a natural, if extremely rare, sequence of gravitational interactions could explain the path. Meanwhile, independent researchers aligned with Harvard's Smithsonian Center for Astrophysics argue that the combination of low inclination, clean trajectory, and synchronized timing across planetary orbits crosses from unlikely into implausible without intervention. As of mid-October, deep space tracking confirms the object's orbital fit with remarkable precision, and as it approaches its perihelion on October 29th, hidden behind the Sun, the trajectory will tighten even further. Any deviation after re-emergence will be immediately noticeable. Even a change of 0.05 degrees will stand out against the current astrometric model. That's why this plane alignment is not just a curiosity, it's a fuse. When an object moves this cleanly, every anomaly after its solar pass becomes a potential signature of intent. Trajectory analysis isn't just about where something moves, it's about when. For most interstellar objects, encounters with planets are random, poorly phased and without discernible rhythm. 3i Atlas is threading a needle. Its approach path is synchronized with multiple planetary positions in a way that orbital statisticians are calling clockwork. The sequence began months ago. In late June, the object crossed the orbital distance of Mars, not the planet itself, but within a timing window of less than 2 days of a near-opposition alignment between Mars and Earth. In August, it swept through a region where Earth's orbital vector pointed almost directly toward its trajectory, maximizing observation opportunities but also theoretically minimizing Doppler detection windows for radio signals aimed along its path. Then in October, just weeks before perihelion, it reaches a geometry where Earth, Mars and Jupiter are arranged in a near-perfect gravitational alignment. This isn't about conjunctions in the astrological sense. This is orbital mechanics. It means that if a maneuvering object wanted to pivot after perihelion toward one of the major planets, it would be passing through the ideal corridor. The timing lines up not to months, but to days. This is where the debate intensifies. For natural objects, such synchronization is possible, but improbable. The combination of ecliptic alignment and synchronized planetary phasing is something that typically emerges only through long chains of coincidence. For a controlled object, however, it's exactly the sort of trajectory you would expect. Minimal energy expenditure, maximum strategic positioning. The October 29th solar conjunction amplifies the stakes. When the object moves behind the Sun from Earth's perspective, it enters a window of total observational blackout lasting several days. No optical or radar tracking is possible. No telescopes can see it. This creates a maneuver window where any course change would be hidden from direct observation. If the trajectory after re-emergence diverges from the pre-conjunction model, that blackout becomes the moment everything changed. Engineers have run scenarios. A perihelion passed this close to the Sun provides a massive gravitational boost, the foundation for what's known as an Oberth maneuver. If any propulsion system exists on or within the object, a short burn at this point could redirect it toward an Earth or Jupiter intercept in 2026. And because its orbit lies almost perfectly in the ecliptic, even a modest impulse could dramatically reshape its path. Natural explanations do exist. Orbital phasing of this kind can occur through chance alignments of multiple planetary positions over decades, but the stacking of anomalies matters. Low inclination, synchronized phasing, exact perihelion behind the Sun, and delayed Coma activation. Each one adds weight to the argument that this may not be just another icy visitor. Researchers at ESA's European Space Operations Centre and the NASA Jet Propulsion Laboratory are preparing for what happens after it emerges in early November. The first few trajectory updates will be decisive. Even a subtle velocity change will propagate into thousands of kilometers of positional difference by January. If its path shifts toward Earth or Jupiter, it won't be accidental, not at these scales. This synchronized planetary geometry has many calling it a silent test. It's as if the solar system itself has been arranged for an experiment, one that began decades ago, when the object was still far beyond the heliosphere. If this is coincidence, it is extraordinary. If it's not, then the blackout window may not just be a celestial event, it may be an inflection point. In late August, just as 3i Atlas brightened beyond magnitude 15, observatories around the world began reporting an odd asymmetry in its coma, the hazy envelope of gas and dust surrounding a heated nucleus. Normally, comets develop symmetric comae that flow outward in multiple directions as volatiles sublimate. This isn't just theory, it's basic thermodynamics. When sunlight hits the surface, ices vaporize and release jets that produce a roughly isotropic, or at least balanced, pattern of outflow. What was seen here was nothing like that. High-resolution imagery from European Southern Observatory and narrowband photometry from Lowell Observatory revealed a strongly forward-biased coma, a jet structure aligned not randomly, but precisely along the object's velocity vector. In other words, the gas wasn't venting in all directions, it was flowing with the motion of the object. The morphology looked almost like a propulsion plume, narrowing rather than diffusing. Coma asymmetry is not unknown, but the degree here is what alarms researchers. Modelling shows that nearly 87% of the outgassing momentum appears aligned forward, leaving only a weak diffuse tail behind. For a natural comet, such a concentrated thrust in the direction of travel would produce significant non-gravitational acceleration. Yet precise astrometric tracking by the Deep Space Network has found no measurable deviation from its predicted path at the 10 to the -5 meters per second squared level. That means either the mass of 3I Atlas is extraordinarily high, dampening any acceleration, or the gas is being expelled in a way that cancels its own effect. Neither scenario fits comfortably with ordinary cometary physics. Spectroscopic studies have added another layer of strangeness. The outgassing composition isn't water-rich like typical long-period comets. It's dominated by CO2 volatiles with only faint traces of water and, more unusual, an emission line complex associated with metallic nickel vapor, without the corresponding ion signatures usually found in cosmic dust. That chemical profile is extremely rare. Nickel is heavy. Getting it to vaporize requires sustained heating, well beyond what sunlight alone typically achieves at these distances. This kind of forward-directed high-temperature venting suggests not a random jetting surface, but either a very stable geometry where only one active region is emitting, or a controlled configuration, perhaps vents or structures aligned with the direction of travel. Thermal models struggle to explain how such directional outgassing could persist over weeks without chaotic tumbling. A natural object this active should be rotating, jittering, and experiencing torque. Yet the Coma has remained geometrically stable. Polarimetric analysis indicates the jet direction has varied by less than 3 degrees over 40 days. For comparison, most comets vary by tens of degrees over the same time due to nucleus rotation and uneven heating. This is why dynamicists are paying so much attention to this single quiet feature. If the gas flow is producing thrust, and if the object is deliberately compensating for it, whether through mass distribution, structure, or active control, then what we're looking at isn't a simple comet. It's something that behaves like it wants to maintain a clean path. The forward Coma isn't just a curiosity. It ties directly into the maneuver window at perihelion. If thrust is being generated, even passively, it could be used to perform an Oberth-like boost without external engines, or with engines hidden beneath the cloak of natural gas emission. Such a maneuver, conducted behind the Sun, would be effectively invisible until the object reappears in early November. And here's the critical detail. The forward vector of the Coma already aligns with the Sun relative path it would need to take for an Earth-Jupiter transfer trajectory in 2026. If this is just a coincidence, it's another stack to top all the others. The ecliptic alignment, the timing corridor, the blackout window, and now the Coma thrust vector. Astrophysicists and propulsion specialists are quietly debating this behind closed doors. The term non-cooperative vehicle, normally reserved for defunct spacecraft drifting through orbit, has appeared in internal discussions. No one is claiming definitive evidence of technology, but the dynamics being observed are starting to look less like nature and more like navigation. One of the most baffling features of 3I Atlas is how little its orbit is being affected by its own outgassing. In comets, like 2I/Borisov or C/1995-01, Hale-Bopp, sublimation near the Sun creates measurable non-gravitational forces. These show up as subtle but unmistakable deviations in the orbit, shifts of a few meters per second in velocity, accumulated over weeks. These forces are diagnostic. They let astronomers estimate mass, density, and activity level. With 3I Atlas, the Coma is vigorous, bright, and highly directed. It's releasing gas at rates that, by conservative thermal models, should impart millimeters per second of acceleration per day, easily measurable at current tracking precision. Yet deep space ranging, radar echo timing, and orbit determination solutions show essentially no drift. Its trajectory remains rock solid. That leaves only two explanations. Either the mass of the object is far higher than anyone expected, or the thrust is being neutralized in ways that don't match ordinary sublimation. Let's look at the numbers. Based on Coma brightness and CO2 sublimation models, current gas output is estimated between 5 × 10 to the power of 4 and 1 × 10 to the power of 5 kilograms per second. For a typical nucleus density and size, that level of venting would cause measurable changes in its orbit within weeks. But so far, the orbital fit hasn't shifted by more than 0.0001 astronomical unit in projection. Reverse engineering the implied mass leads to extraordinary figures. To resist the recoil of that much outgassing, the nucleus would need to have a mass of at least 10 to the power of 13 kilograms, possibly higher, putting it in the mass range of a large asteroid, not a fluffy comet. This would make 3I Atlas one of the densest interstellar bodies ever detected if natural. The shape of the outgassing curve complicates matters further. Instead of fluctuating chaotically as the body rotates, the activity is remarkably stable, suggesting either 1. An internal structure with extraordinary mass distribution resisting torque, 2. A tumbling rate so slow it borders on stationary relative to its orbit, 3. Or active stabilization. None of these fit comfortably with the behavior of ordinary volatile-rich bodies. There's also a discrepancy in thermal signature. Infrared measurements from the James Webb Space Telescope show a nucleus temperature curve that doesn't match standard sublimation models. The surface seems to be radiating less energy than expected given the measured gas output, suggesting either deep internal reservoirs or an energy source that isn't purely solar. If the object really is this massive, it has another implication. It could mask propulsion events during perihelion. A small burn hidden beneath the noise of gravitational assist wouldn't leave the sort of telltale kinematic fingerprints that lighter objects reveal. This would make detection of any maneuver extremely difficult until weeks later, when the positional difference accumulates into a measurable deviation. The idea of mass as camouflage isn't science fiction. It's a known principle in astrodynamics. The heavier the object, the harder it is to detect subtle course corrections in real time, with perihelion falling behind the Sun a blind spot. Even a precisely timed impulse could be concealed. This is why analysts at NASA Jet Propulsion Laboratory are preparing for rapid post-conjunction orbital solutions. The moment it re-emerges, they'll compare its position to high-precision ephemerids generated before the blackout. Any difference larger than a few hundred kilometers will be a red flag. The mass discrepancy isn't just a scientific curiosity, it's a shield, either a natural one that makes the object harder to study, or a deliberate feature of something designed to pass unnoticed until it's too close to ignore. Among all the anomalies surrounding 3I Atlas, none has rattled the scientific community more than its chemical fingerprint. Orbit can be debated, Coma behavior can be modeled, mass can be estimated. But chemistry leaves harder edges. It reveals something about origin, how and where an object formed, and sometimes how it has been altered. What astronomers are seeing doesn't match anything on record. The standard volatile composition of comets is well understood. Water vapor usually dominates, mixed with CO2, CO, methanol, ammonia, and trace hydrocarbons. Metallic vapors often include iron, magnesium, sodium, and nickel in roughly solar proportions. Even exotic interstellar visitors like 2I/Borisov fit, more or less, within this chemical pattern. They may vary in ratios, but they don't defy the framework entirely. 3I Atlas is doing exactly that. Spectral data collected from multiple facilities, the James Webb Space Telescope, European Southern Observatory, WM Keck Observatory, and several independent radio interferometers, reveal an extraordinary imbalance. CO2 dominates at levels almost 10 times greater than water vapor, even as the object warms near the Sun. That's already strange. But stranger still, high-resolution emission line spectra show pronounced nickel vapor lines with almost no detectable iron. This is not a subtle anomaly. Nickel and iron are cosmically married. They form together in stellar cores, they travel together in dust grains, they condense together in planetesimals. They are forged in the same stellar environments, locked in nearly constant abundance ratios. For iron to be missing while nickel is abundant requires either a highly specific and rare stellar formation environment, a natural separation process so extreme it's effectively unheard of in known cometary evolution, or some form of deliberate material selection. The nickel lines are sharp and persistent. JWST data indicate their thermal profile corresponds to temperatures well above the sublimation range of common cometary volatiles, meaning the nickel is being released from an intensely heated surface or structure. Yet the infrared emission from the nucleus suggests something paradoxical. Its surface temperature isn't high enough to explain this naturally. Something is heating or vaporizing nickel selectively without producing the broad thermal signature of a uniformly warming body. Iron's absence deepens the puzzle. In every previously studied comet, iron is present in amounts that track nickel closely. Iron atoms produce easily identifiable emission features in the near-infrared and visible ranges. Here, those features are silent. If the iron is present at all, it is at levels below detection thresholds, or it's somehow bound in a non-emitting phase. For planetary scientists, there are only a few natural ways this could happen. One involves an object formed in an unusually metal-poor region, with peculiar condensation chemistry, but that would make this interstellar visitor an extreme outlier, the kind of statistical rarity one expects once in centuries, if ever. Another involves iron being buried deep beneath a crust, while nickel is concentrated near the surface. But for that to persist through interstellar travel and solar heating is nearly impossible without the object breaking apart or rebalancing its chemistry. Then there's the third possibility, the one people are careful not to say too loudly in press briefings: engineered composition. Nickel's properties make it ideal for high-temperature structural components. It's strong, resistant to corrosion, and can withstand intense solar heating near perihelion. If a structure were deliberately designed to survive a solar slingshot maneuver, nickel would be one of the smartest materials to use, and CO2 would be a logical volatile to carry, cheap to store, easy to vent, and capable of producing thrust without revealing ion signatures that stand out on spectroscopic scans. Combine those two features, a nickel-dominant structure and CO2-controlled venting, and you get something that looks, from a distance, almost like a comet, but isn't. It would glide on a clean orbit, shield itself thermally, and use perihelion as a perfect moment to change direction without revealing a propulsion signature. This is why many in the planetary science and CTI communities are describing the chemistry as the single most suspicious anomaly so far. Orbital coincidences can be argued away as rare. Coma asymmetry can be stretched to fit extreme physical models. But chemical composition is far harder to wave off as coincidence. It is either the product of an exceptionally rare natural environment or the residue of deliberate construction. Adding to the unease is the timing of these detections. The nickel emission lines began to strengthen in mid-October, just days before the perihelion blackout. CO2 production has steadily increased, aligned precisely along the object's velocity vector, with almost no rotational modulation. This level of stability in venting isn't how nature behaves. Real comets spin, flare, wobble. They don't hold a jet stable for weeks with sub-degree variance. What this means is simple but profound. If a maneuver is planned, natural or otherwise, the ingredients to execute it are already in place. A nickel shell would let the object withstand a close solar pass. CO2 would provide the propulsive impulse, and the sun would blind us to everything happening in real time. When the object re-emerges in early November, we'll know if this chemical signature was just an echo of an exotic formation history, or the fingerprint of a machine hiding in plain sight. For months, orbital analysts have been focused on a single date: October 29th, 2025. On that day, 3i Atlas will pass directly behind the Sun from Earth's perspective, reaching its perihelion, its closest approach to our star. Normally, such alignments are routine. Objects slide behind the solar disk, disappear from view for a few days, then return on their outbound leg. But for this particular object, the timing, geometry, and physics combine into something far more consequential: a perfect cloak for any maneuver. From October 28th to roughly November 4th, depending on solar elongation, every ground-based telescope and radar system will lose direct line of sight to the object. Even space-based assets operating near Earth will be effectively blind. The sun's glare will wash out optical imaging, its radio noise will saturate tracking frequencies, and its plasma will corrupt signals beyond reliable recovery. This solar cover window is not merely a gap, it is a blackout. For that period, 3i Atlas will be unobservable, untrackable, and free to do whatever it's going to do. This would matter less if the object's orbit were unremarkable. But the perihelion alignment is exact. The object's hyperbolic trajectory crosses the ecliptic plane at nearly zero inclination, and its perihelion distance is close enough to maximize the Oberth effect, the physical principle that allows a spacecraft to achieve the greatest change in velocity by firing engines at its closest point to a gravity well. In engineering terms, it's the most efficient place in the entire solar system to change course with minimal energy. Analysts at NASA Jet Propulsion Laboratory, European Space Agency, and independent astrodynamics groups have simulated dozens of scenarios. A delta V of only 90 meters per second at perihelion could tilt its outbound trajectory toward Jupiter, setting up a flyby in late 2026. A delta V of around 150 meters per second could bend it toward the Earth-Moon system within a year. To put that in perspective, even a relatively small engine on a modest structure, or a well-timed venting of stored volatiles like CO2, could achieve that. The unsettling part is how invisible such a maneuver would be. Under normal conditions, radar ranging and Doppler tracking would pick up even small changes in velocity. But during solar conjunction, no such tracking is possible. The Deep Space Network cannot maintain lock on a target this close to the Sun due to intense plasma interference. Radio signals scatter, Doppler precision collapses. This means that the object could perform the most critical burn of its entire journey, while the solar system's best sensors are effectively blind. Historically, this kind of window has been used by space agencies to perform delicate trajectory correction maneuvers for their own probes. It's a known opportunity. The difference here is that the object in question isn't under any human agency's control, at least not one we can confirm, and it's moving with a precision that so far has looked less like a tumbling comet and more like something preserving its trajectory intentionally. If the object does nothing, it will continue outbound on its predicted hyperbolic escape path, leaving behind a spectacular but natural mystery. But if it does something, even something subtle, we won't know until days later. The first hint will come when it re-emerges on the other side of the Sun. Orbit determination teams will compare its new position against high-precision pre-conjunction predictions. Any discrepancy larger than a few hundred kilometers will reveal a maneuver. This is why the first post-perihelion tracking window in early November is already scheduled as an international coordination event. The European Space Operations Centre in Darmstadt, the NASA Jet Propulsion Laboratory in Pasadena, and ground stations in Australia, Spain and Chile will all attempt to reacquire the target as soon as it clears the Sun's interference zone. For a few hours, the world's most powerful sensors will be aimed at a single patch of sky. Every kilometre of offset, every arc-second of deviation will matter. The geometry also means that if the object were to make a significant course change, it could effectively vanish for weeks. A well-placed burn could redirect it along a path that takes it out of the predicted recovery corridor. In such a case, reacquisition could be delayed, or, in a worst-case scenario, missed entirely. The possibility of losing track of an interstellar object after it performed a hidden burn at perihelion isn't theoretical. Analysts have run the numbers. If it changes course by more than 0.07 degrees during the blackout, it could exit the planned search cone altogether. This is where the earlier anomalies begin to converge. The mass discrepancy means even a small burn would be difficult to detect quickly. The nickel composition suggests a structure that can survive extreme thermal stress. The forward coma provides a perfect cover for CO2-based thrust. The precise ecliptic alignment maximizes maneuver efficiency. It's a carefully arranged chain of physical circumstances that, together, give this object an unprecedented opportunity to change direction without being seen. Governments and scientific agencies have been restrained in their public statements. Official press releases frame the blackout as a temporary observational gap, but behind closed doors this period is being treated as a critical inflection point. Teams are preparing rapid response protocols, and there are rumours, unconfirmed but persistent, that several classified optical assets will attempt solar edge tracking to minimise the gap. The truth is simple and sobering. For several days at the end of October, humanity will have no idea what 3I Atlas is doing. Whether it remains a silent, extraordinary comet or becomes something entirely more complex depends on what happens in that invisible corridor around the Sun. The solar cover isn't just a moment on a calendar, it's the fulcrum of the entire story. For nearly a decade, Juno has been orbiting Jupiter, rewriting our understanding of the gas giant's interior, magnetic field, and ancient history. It was never designed to leave. It has no fuel to return to Earth, no path beyond Jupiter. But in the last weeks of 2025, the probe's quiet, elliptical dance around the planet has taken on a new significance. Behind closed doors, mission planners at NASA Jet Propulsion Laboratory and NASA Marshall Space Flight Center have been modelling a radical maneuver, redirecting Juno toward 3I Atlas if the object's post-perihelion trajectory bends toward Jupiter. It would be a one-way journey, a suicide mission for the spacecraft. But it could give humanity the only chance of a close-range observation before the object either escapes or does something even more unexpected? This possibility only exists because of how precisely 3i Atlas has threaded the inner solar system. Its trajectory, depending on what happens behind the Sun, could take it on a course that swings outward into Jupiter's orbital region by late 2026. That is where Juno sits, not in deep space, but in a long, looping orbit that occasionally places it in perfect position for a gravity assist maneuver. If 3i Atlas does indeed shift its course toward the gas giant, the geometry becomes almost eerie in its alignment. Juno could intercept or at least make a close pass with modest adjustments, but the costs would be absolute. To break its stable orbit and chase the object, Juno would have to expend every remaining drop of fuel, abandoning its science orbit permanently. There would be no return to Jupiter studies, no continued mapping of its magnetosphere. A probe that has spent years studying the largest planet in the solar system would be effectively hurled into deep space, riding the tail of a mystery. The decision isn't simple. On one hand, Juno has already outlived its primary mission, and its extended mission was scheduled to run only a few more years. It has delivered extraordinary science. On the other hand, redirecting it isn't guaranteed to succeed. 3i Atlas may not even take the Jupiter corridor. If it does, its velocity will be enormous. Juno wouldn't be able to match speeds. It would simply make a fast, high-speed pass, collecting whatever data it could during a brief encounter measured in minutes. But those few minutes could change everything. Juno's instruments, though old, are still capable of high-resolution magnetometry, spectroscopy, and plasma analysis. If the object is artificial, even in part, the probe could detect its electromagnetic emissions, thermal signature, surface reflectivity, or other anomalies no telescope from Earth could ever see. Even a blurred snapshot from a few hundred kilometers could answer questions the world has been circling for months. Mission engineers have already run the numbers. If Juno initiates a trajectory correction before the end of March 2026, it could line up a flyby window between November and December 2026. This is assuming 3i Atlas takes a clean outbound trajectory past Jupiter. The required delta-v would consume nearly all of Juno's maneuvering reserves. After the encounter, the spacecraft would drift into heliocentric orbit, effectively ending its life as a functioning planetary probe. It's not just a technical debate, it's a philosophical one. Do you sacrifice a successful, still operational mission to chase something that might, or might not, be the most important interstellar object ever detected? Do you gamble decades of work for a single shot at contact, or do you let the object pass, preserving what remains of Juno's original science program? Among mission scientists, the opinions are divided. Some argue that Juno's instruments are too limited to justify the risk, that the data, while interesting, may not reveal anything conclusive. Others point out that no other spacecraft is remotely positioned to make an intercept. If the object bypasses Earth entirely and heads for deep space, this might be humanity's only chance to get close. The decision is complicated by the uncertainty of the solar cover. Until the object emerges in early November, no one knows which path it will take. If it remains on its predicted hyperbolic outbound, the Jupiter corridor is irrelevant. But if it tilts, even slightly, toward a Jupiter-bound trajectory, the choice will come fast. Analysts believe the go-no-go decision window for Juno could close within 2 weeks of re-emergence. That's how little time the agencies will have to decide. There are also technical limitations. Juno wasn't built to chase fast interstellar targets. Its communications array, power systems, and instruments were designed for a polar orbit around Jupiter, not the deep cold of interplanetary pursuit. If it goes, it will be flying blind for much of the journey, with limited opportunities for course correction. Mission Control would effectively be launching it into the dark, hoping the calculations hold. Yet, despite these constraints, momentum is building inside the engineering community. A one-way intercept wouldn't just be symbolic. It would be the first human-built machine to approach a confirmed interstellar visitor with a potential technological signature. It would be a message. We didn't just watch, we followed. Whispers inside the SETI and planetary defense circles suggest that if 3i Atlas makes the Jupiter turn, the sacrifice is likely to be approved. Not because it's guaranteed to succeed, but because the stakes are too high not to try. A mission that began as a study of Jupiter's magnetic field could end as the tip of a spear aimed at a mystery older than any planetary program. Juno's fate now hinges on something entirely outside its control: what 3i Atlas does while hidden behind the Sun. A single course correction in those invisible days could turn an aging probe into humanity's first interstellar scout, or leave it forever circling a distant giant, watching the opportunity fade into the cold. When 3i Atlas slips behind the Sun on October 29th, Earth-based telescopes will go blind. But humanity's eyes won't all be on this side of the solar system. On the other side, positioned advantageously along different lines of sight, a handful of robotic explorers may keep partial watch. Chief among them are the Mars Orbiters and JUICE, the European spacecraft making its way toward Jupiter. These assets are about to become the front line of the most tightly coordinated observation campaign ever mounted for a single object. The timing is critical. In early October, several Mars Orbiters, including Mars Reconnaissance Orbiter, MAVEN, and Trace Gas Orbiter, began retasking their instruments to gather long baseline astrometric measurements of 3i Atlas. Their vantage point is offset from Earth's by tens of millions of kilometers, giving them an angle on the object that Earth simply can't achieve during solar conjunction. Even when Earth goes blind, Mars won't experience the same level of glare. The object will pass close to the edge of the solar disk from Mars's perspective, not directly behind it. That sliver of visibility may prove decisive. This means that while Earth's observatories fall silent, Mars will still be able to track subtle shifts in position, brightness, and outgassing activity. Not with full clarity, but enough to keep a thread of data alive during the blackout. Engineers at European Space Agency and NASA Jet Propulsion Laboratory have spent weeks optimizing tracking sequences. A small fleet of orbiters, originally designed to study Mars, will be pointed toward deep space, becoming improvised sentinels in the most critical moment of the timeline. Then there's JUICE, the Jupiter Icy Moons Explorer. Though still en route to its target, its trajectory places it at an advantageous angle during and after the perihelion blackout. While it's far from the object's actual position, its line of sight to the post-conjunction arc will be clearer than Earth's for several days. If 3i Atlas performs a trajectory change, JUICE could detect the first measurable offset before ground telescopes even reacquire it. These off-Earth observations are not just a backup plan, they are the decisive layer in determining whether the object behaves like a natural body or executes something controlled. Astrometric shifts as small as tens of kilometers will be detectable by combining data from Mars, JUICE, and deep space assets. The goal isn't high-resolution imagery, it's timing and trajectory. Even the smallest velocity change during perihelion will manifest in positional discrepancies by early November. The data race will be fierce and time-sensitive. Once the object emerges, Earth's major observatories, including the Very Large Telescope, Greenbank Observatory and the Allen Telescope Array, will snap back online. Their first priority won't be to study the coma or spectrum, it will be to compare predicted trajectory versus actual position. That single delta will tell everyone whether something happened behind the Sun. Here's why this matters. If a maneuver occurs, its scale will determine everything that follows. A tiny shift, a few dozen meters per second, would indicate subtle course trimming, possibly a passive adjustment or a natural pressure differential. A medium-scale burn could tilt the outbound arc toward Jupiter, setting up the possible Juno intercept window. A larger burn could tilt it toward Earth's orbital zone, an outcome that would trigger a completely different and likely more intense response. These distinctions are critical because the object's massive inertia makes small burns hard to detect in real time. But with precise timing and distributed sensors, analysts can extract meaningful signals from tiny positional shifts. This is why the International Scientific Network is treating this like a coordinated operation rather than a passive observation. Data synchronization protocols are being updated daily. Ground stations in Australia, Spain, and South America are standing by to catch the earliest signals once it clears the solar limb. Mars and JUICE will feed in the cross-angle measurements. Supercomputers will run real-time orbit updates. And behind this flurry of scientific coordination lies something more strategic. Several space agencies are quietly preparing classified contingency models for different trajectory outcomes. While the public is focused on whether the object is natural or not, operational planners are looking at impact probabilities, deflection scenarios, and early intercept feasibility. Even if the chance of a deliberate or Earth-directed path is small, the cost of being unprepared is infinite. The public won't see these models. But what they will see is how quickly information moves once the object reappears. There will be a sharp, perhaps dramatic moment in early November, when the world learns whether it stayed on its predicted outbound track or diverged. That moment will belong not to any one observatory, but to a network of machines scattered across the solar system sharing one task: don't lose the object. The irony is sharp. For decades, Mars orbiters and JUICE were built to study other worlds. None of them were launched with the mission of tracking something possibly intelligent. And yet, here they are, playing a role no one foresaw, watching an object that may be more than just rock and ice. If the data they gather confirm a maneuver, they will not just record history, they will define it. Because from that moment forward, everything, political, scientific and cultural, will pivot. The object's mystery will no longer be a question of if, but of why. For months, the astronomical community has been moving in cautious lockstep: observe, collect, model. But as 3i Atlas nears its critical perihelion blackout, the unified front is beginning to fracture. What started as a measured, quiet analysis has now turned into one of the most intense scientific divisions in modern history. The object's trajectory, composition and behaviour have forced researchers into two sharply opposed camps: those who still insist it can be explained through natural phenomena, and those who now suspect something far less ordinary. On one side are the conservatives, planetary scientists, comet physicists, and orbital dynamicists who see the anomalies as extraordinary, but not supernatural. They argue that nature is messy and unpredictable, and that given enough time, rare events happen. In their view, 3i Atlas is a once-in-a-millennium comet, a CO2-dominated nickel-rich fragment from a chemically exotic star system, arriving at a perfectly timed angle due to gravitational focusing and orbital coincidence. They point out that past anomalies, like 1I/Oumuamua's non-gravitational acceleration, were eventually tempered by new models, even if not fully explained. To them, the forward Coma, ecliptic alignment, and WOW-era trajectory overlap are improbable, but not impossible. In long, careful papers and late-night conferences, they remind their peers, extraordinary claims require extraordinary evidence. Until a direct signal or unmistakable technological signature is detected, this must be treated as a comet. A very strange comet, yes, but still within nature's jurisdiction. Then there's the other side, a coalition of SETI researchers, propulsion specialists and astrophysicists who have spent their careers studying low-probability phenomena. For them, the string of coincidences is too clean, too symmetrical, too perfectly timed. They point to the ecliptic plane alignment, which effectively sets the object on a navigational corridor. The nickel-dominated composition, suspiciously well-suited for withstanding solar heating. The Coma vector, aligned with the direction of travel like a controlled exhaust. And the perihelion blackout, a maneuver opportunity straight out of engineering handbooks. They argue that natural explanations are being stretched thin to preserve a sense of normalcy. In their private conversations, a phrase has begun to circulate: if this isn't technological, it's the best impersonation of technology the cosmos has ever pulled off. The debate has spilled beyond academic journals. At a private symposium organised by the International Astronomical Union in early October, discussions became heated. Some planetary scientists accused the SETI camp of sensationalism, of letting the allure of the first contact scenario override rigorous caution. The city researchers countered that ignoring converging anomalies simply because they're uncomfortable is itself unscientific. One senior astrodynamicist reportedly said, "We're arguing probability distributions while the object is literally moving into the sun's blind spot. The divide isn't just philosophical, it's operational." The conservative camp wants to wait, collect post-perihelion data, and refine natural models. The SETI-leaning camp is pushing for aggressive tracking, rapid response observation windows, and, if the trajectory changes, the immediate mobilization of all available space assets, including redirection of missions like Juno. This clash is shaping the actual observation strategy. The planetary science networks favour high cadence, long-term monitoring after re-emergence, assuming slow and predictable orbital behaviour. The CT and propulsion analysts favour rapid, flexible targeting, expecting an early sharp deviation if a maneuver occurs. The disagreement over how to prepare is growing more visible as the blackout window approaches. Publicly, institutions are still speaking with one voice. Official press releases use neutral language, unusual object, ongoing analysis, no evidence of artificiality. But behind the scenes, the tone is shifting. Leaked internal memos from both American and European space agencies hint at contingency tiers, depending on the scale of post-perihelion trajectory deviation. The very existence of such plans implies that agencies are taking the more extraordinary possibilities seriously, even if they won't say it out loud. This fracture is also psychological. For some scientists, acknowledging the possibility of technological origin feels like stepping into dangerous territory, a place where science collides with geopolitics, public hysteria, and deep cultural fear. For others, not acknowledging it feels like deliberate blindness. A renowned planetary chemist reportedly said during a closed discussion, "I've spent my entire career studying comets. This doesn't behave like one the coming weeks are, in many ways, a stress test for the scientific process itself. Every observation made after the blackout will be poured through two lenses, one looking for natural explanations, the other searching for signals of control. If the object re-emerges exactly where predicted, the conservative camp will gain ground, arguing that the burden of proof remains unmet. If it doesn't, if the trajectory bends, even slightly, or the entire discussion will tilt, and fast. The scientific divide is not just about this object. It's about what happens when the unknown steps too close to home. If 3I Atlas is natural, it will be remembered as a strange but illuminating visitor. But if it isn't, this debate will mark the moment the world's scientific institutions crossed a psychological Rubicon. The moment 3I Atlas became a trending topic, the scientific debate stopped being contained to labs and observatories. What began as quiet chatter among astronomers is now an open global phenomenon, unfolding in real time across social media, television, forums, podcasts, live streams, and news cycles. The public isn't just watching, it's participating, speculating, theorizing, and in many cases panicking. In early September, when the object's trajectory was revealed to align almost perfectly with the coordinates of the 1977 narrowband signal, hashtags began flooding X and YouTube. Hashtag Atlas Object, hashtag 1977 signal, hashtag contact window, and the darker hashtag perihelion event. Conspiracy forums exploded overnight. Within a week, clips claiming government cover-ups had millions of views. Entire digital subcultures formed around the idea that the object is not just interstellar, it's intelligent. What's different this time is how fast information spreads and mutates. When 1E Oumuamua passed through the solar system in 2017, discussion remained relatively niche. Scientists talked among themselves, the media reported, and public interest faded. But now, nearly a decade later, the world is far more interconnected. Real-time orbital data is being mirrored on amateur sites. Enthusiasts are running their own simulations. Analysts on live streams are overlaying comet trajectories with star maps and claiming to have decoded hidden patterns. One of the most viral theories suggests that the perihelion blackout isn't just a coincidence, it's the moment of arrival. A coordinated movement online portrays the October 29th solar conjunction as a deliberate insertion window for something entering the inner solar system unseen. Millions of posts count down the days like a cultural event. Others spread more fearful narratives, predicting earthbound trajectories or signal activations. None of it is verified, but in the public mind, speculation often moves faster than evidence. The absence of clear official communication is pouring fuel on this fire. Space agencies have issued carefully worded statements emphasizing that no evidence of artificiality exists, but their restraint has only made some corners of the internet more suspicious. Leaked tracking data, often taken out of context or fabricated, circulates freely. Grainy telescope footage is stitched into videos claiming proof of thrusters, lights, or beacon emissions. Fact-checkers are working overtime, but the volume of misinformation outpaces them. Meanwhile, SETI organizations and academic groups trying to provide calm, data-based updates are caught in the middle. Their explanations are drowned out by sensationalism. A few respected scientists who have acknowledged that the object is highly unusual are being quoted, misquoted, and turned into unwilling figureheads for alien contact narratives. Some are receiving threats. Others are retreating from public communication altogether. But it's not just fear. Fascination is everywhere. Humanity has always stared into the sky and projected its hopes, fears, and myths onto what it can't explain. In some communities, Three-Eye Atlas is being mythologized almost in real time. Online groups speak of it as a messenger, a watcher, even a returning signal. Digital art, music, stories, and short films are already flooding creative spaces. For many, this event has tapped into something primal, the idea that the universe might finally be answering back. Governments are walking a tightrope. Releasing too much information could accelerate panic. Releasing too little could validate the more conspiratorial narratives. Intelligence analysts and sociologists have privately referred to the perihelion blackout as a belief inflection point. Once the object disappears behind the sun, with no new data for several days, the vacuum will be filled by speculation, not by science. The phenomenon is already affecting markets, politics, and culture. Defense stocks in several countries have ticked upward. Faith communities are holding vigils, framing the event through religious prophecy. Tech companies are leveraging the attention to promote deep space monitoring apps and satellite feeds. Politicians are making statements, some measured, others opportunistic. At the center of all of this sits an object silently hurtling toward perihelion, neither confirming nor denying anything. It doesn't need to. Its very existence has already split public discourse into belief systems, each feeding on uncertainty. Psychologists warn that the return after the blackout could be even more volatile. If the object emerges exactly where predicted, some narratives will collapse. But if it doesn't, if even a small deviation is detected, speculation will metastasize instantly. The debate will leave the realm of science entirely. It will become cultural, political, even existential. And perhaps most unsettling of all, no matter what happens, the world will remember the October blackout not just as an astronomical event, but as the moment it collectively held its breath, waiting for something, or nothing, to emerge from behind the sun. If Three-Eye Atlas were to maneuver during the perihelion blackout and display clear signs of control, the world would wake up to a question it has never truly answered. Who speaks for Earth? For all of humanity's fascination with extraterrestrial contact, there is no binding, globally coordinated protocol for responding to an object that might be technological in origin. Treaties exist for war, trade, disaster relief, even asteroid impact mitigation. But when it comes to first contact, humanity's playbook is a patchwork of outdated agreements, non-binding statements, and scientific courtesy protocols drafted in an era when contact was considered hypothetical, distant, and unlikely. The closest thing to a framework is the post-detection protocol drafted decades ago by the International Academy of Astronautics and endorsed loosely by several SETI groups. It states that any confirmed detection of extraterrestrial intelligence should be publicly shared, scientifically verified, and communicated through international channels, preferably via the United Nations Office for Outer Space Affairs, UNOOSA. But that document was written for radio signals, the quiet detection of something far away, not the sudden arrival of an object inside the solar system with a trajectory we can track in real time. In practice, this means that no one actually has the legal or operational authority to coordinate a global response. If Three-Eye Atlas performs a maneuver that confirms technological control, the first interpretation won't come from the UN. It will come from whichever agency or government gets the data first. That could be NASA. It could be ESA. It could even be a private observatory, since orbital tracking is not the exclusive domain of governments anymore. This is why diplomats, military analysts, and SETI researchers have quietly begun referring to this scenario as the protocol vacuum. In the hours or days after such a maneuver, multiple actors would scramble simultaneously to issue statements, hold press conferences, or assert jurisdiction over the event. Each would be operating from different priorities. Scientific agencies would want open data and verification. Governments would prioritize security, control of communications, and maintaining public order. Private networks would leak raw data in real time, forcing institutions to respond reactively. Military commands would assess potential threat profiles before anything else. The risk is not just confusion, it's fragmentation. With no unified process, the narrative could split across competing voices before any coordinated strategy exists. Even a few hours of mixed messaging, especially in a world already saturated with speculation and fear, could shape global perception permanently. The UNANSWERD mandate technically includes the role of facilitating international cooperation in space affairs, but it has no enforcement power, no standing military, no rapid communication framework. Its protocols are built for diplomatic consultation, not real-time existential events. In an internal review quietly circulated in 2023, UNANSWERD itself acknowledged that the existing mechanisms would be insufficient to manage public expectations and international coordination in the event of confirmed contact with non-terrestrial intelligence. Intelligence agencies are not blind to this. In the weeks leading up to the perihelion blackout, several major governments have quietly run simulated scenario briefings, not about fighting aliens, but about managing the information flow if the object behaves in ways that can't be explained away. The key question isn't what to do if the object turns hostile, it's how to control the first 48 hours of global reaction. Behind closed doors, legal scholars and policy experts have also been debating a quieter, more uncomfortable question. Who has the right to engage first? If the object were to transmit, or if a spacecraft like Juno were to make a close pass and detect something unmistakable, who would respond? Who would have the moral or legal legitimacy to speak on behalf of a planet with 8 billion people and no unified voice? The lack of a clear answer is not an accident. For decades, first contact was treated as an abstract scenario best left to philosophers and scientists. No one wanted to build a legal framework around something that might never happen. But 3i Atlas has turned the abstract into a countdown clock. The perihelion window isn't just a scientific event, it's a test of governance. Some nations have already begun drafting their own unilateral contingencies, not public, but quietly circulated between defence and intelligence branches. These include early warning protocols, communication control plans, and media blackout scenarios. None of this is coordinated globally. If something truly unprecedented happens, the world will likely respond in fragments before it responds in unison. For scientists, this is deeply frustrating. For strategists, it's dangerous. And for the public, it may be bewildering. In the absence of a shared, trusted protocol, whoever speaks first will shape the entire narrative, whether they are ready to or not. The universe doesn't wait for bureaucracy to catch up. If something emerges from behind the sun and behaves in a way that confirms intelligence, humanity won't have months or even weeks to deliberate. It will have hours. Every story has a pivot and a moment when all the speculation, all the doubt, all the careful probabilities collapse into something real. For 3i Atlas, that moment is approaching like a clock ticking in deep space. The perihelion blackout has set the stage, but it is the re-emergence in early November 2025 that will turn this from a mystery into a defining chapter of history. For months, scientists have spoken cautiously. Words like unusual, anomalous, and statistically rare have dominated their vocabulary. But once the object reappears, those linguistic shields will no longer hold. Numbers will. Trajectories will. Either it will emerge where expected, a strange but ultimately natural visitor, or it won't. And if it doesn't, the world will shift gears overnight. This moment is different from anything humanity has faced before. When Oumuamua passed through the solar system, its anomalies were retrospective, detected after the fact, debated after it was gone. 3i Atlas, in contrast, has given the world a front-row seat to a potential turning point before it happens. We are not looking back. We are waiting, watching, counting down to an event that has not yet unfolded. That anticipation is its own kind of gravity. Agencies across the globe have built parallel observation windows. Radio telescopes, optical arrays, and deep space tracking networks will activate in synchronized timing the moment the object clears solar interference. Some instruments are already warming up to minimize latency. Orbit determination centers in Pasadena, Darmstadt, and Canberra are standing by to ingest the first slivers of post-conjunction data. Even a single astrometric measurement will begin to tell the story. If the position matches predictions to within tolerance, it strengthens the natural explanation. If there's even a small deviation, the numbers will cascade. Models will branch into new trajectories. Simulations will multiply. Within hours, the unknown will be something measurable. The consequences of that measurement go far beyond astronomy. If the trajectory bends, even slightly, toward a corridor leading to Jupiter or Earth, everything downstream accelerates. The scientific debate will implode into a new phase. Public speculation, already boiling, will explode. Political and military institutions currently shadowing the event quietly will step forward. And the absence of clear international protocols will mean that whoever detects and announces the deviation first will own the global narrative for hours, maybe days. That's why the most powerful telescopes and tracking systems on Earth are not just preparing to observe, they are preparing to compete, not maliciously, but in the way nations do when the first glimpse of something unprecedented is at stake. It won't be a single, clean announcement. It will be fragmented. Snippets of telemetry here, leaked orbit data there, agencies rushing to confirm or deny trajectories, independent astronomers posting early estimates online. By the time the first coordinated statement reaches the public, millions may have already seen raw figures, and once that happens, there is no going back. If the object behaves naturally, it will remain an extraordinary, beautiful puzzle, an outlier that rewrites some chapters of cometary science and SETI history, but ultimately stays in the realm of nature. But if it behaves otherwise, the human timeline effectively bifurcates. History before November 2025 and history after it will not be the same. That turning point won't look like a single dramatic broadcast. It will be quieter, stranger. A handful of orbital analysts will see the first numbers drift. A data visualization on a monitor will show a slight kink where a straight line was expected. Someone in a control room will mutter, "That's off." And in that moment, they'll know the narrative has shifted. The most chilling part of this story isn't the possibility of what 3i Atlas might be. It's how little time the world will have to process whatever comes next. No matter the outcome, the object has forced humanity into real-time confrontation with something bigger than any one government, agency or belief system. This is why so many inside the scientific community describe late 2025 not just as a date on a mission timeline, but as a hinge of history. Because whatever emerges from behind the sun won't just define the object. It will define us, how we communicate, how we coordinate, how we respond when something truly unknown moves out of the shadows. There will be no theatrical moment, no countdown clock flashing across the sky, just data, just silence, just the object emerging from solar glare like an answer to a question no one was ready to ask out loud. October 29th, 2025 will pass like any other date on a calendar, but its meaning will stretch far beyond it. The moment 3i Atlas slips into the solar glare, the world will enter a kind of collective silence. Telescopes will lose sight, radar arrays will fall quiet, tracking data will stop flowing, and everything, science, strategy, speculation, fear, will converge on a single reality. We will not know what it's doing. For the first time since its discovery, the object will exist outside our gaze, and then, in the early days of November, it will return. Somewhere in a dimly lit control room, an analyst will watch a telemetry graph stabilize. A pinprick of data, one coordinate, one timestamp, will appear on a screen. That first post-conjunction measurement will carry more weight than months of speculation. If it matches predictions, the story bends one way. If it doesn't, the world tilts the other. There will be no grand announcement in that moment. Just a quiet line of numbers sliding across a monitor, an orbital fit updated, a silence that means everything has changed. All the threads we've followed, the 1977 signal alignment, the surgical ecliptic trajectory, the forward coma, the nickel composition, the timing corridor, the solar cover, the Juno dilemma, the fractured scientific community, and the restless public converge at this point. No new theory will matter, no speculation will stand. What happens after this moment will be written by physics alone. If the object emerges on its expected path, it will remain what it has always been. A mystery wrapped in natural oddities. A comet unlike any other. It will be catalogued, studied, debated for years, and quietly remembered as the strangest visitor our solar system has ever seen. The debates will cool. The sky will return to ordinary silence. Humanity will exhale. But if it emerges off course, and even slightly as everything shifts, the scientific divide collapses into urgency. Public fascination hardens into conviction. Political silence gives way to strategy. Space agencies pivot overnight from study to response. And humanity, ready or not, steps across a threshold it has spent centuries imagining, but never truly prepared for. A world that has always looked outward will suddenly realise that the outward might be looking back. No one knows which story we'll live through, and perhaps that's the most unsettling part. Not the object itself, but the uncertainty it drags behind it like a tail. An unanswered question large enough to hold 8 billion minds hostage for a moment in time. In the end, it won't be decided by theories or press conferences or online arguments. It will be decided by one simple truth written in the mathematics of its new trajectory. When it reappears, the numbers will speak, and everything, science, belief, and history, will have to listen. Late 2025 will be remembered as a turning point not because of what anyone said, but because of what emerged from behind the sun. Whether this moment passes quietly into the archives or cracks open an entirely new chapter of human history depends on something that has no politics, no fear, no narrative: ocean.